Hello. We're getting close to finishing up the content of chapter 30, which deals with the quantization of orbital radii in hydrogen and the quantization of the electron energies. We will study the excitation of electrons in hydrogen as well as the reverse process, de-excitation, sometimes referred to as relaxation. I show a few of the innermost orbitals of the electron, n equal to 1 being the lowest lying one, 2, 3, and 4. The equation for the electron energies is determined by is shown here. It's negative 13.6 electron volts divided by the square of the quantum number, divided by n squared. This table shows what the electron energies are for the first four quantum numbers, 1, 2, 3, and 4. N squared is likewise shown in the middle column. And we divide 13.6 negative by those numbers and obtain the following negative energies. What we will first do is discuss the excitation of electrons. An electron in any one of the orbits possibly can absorb a photon. If the energy of the photon is just right, then that electron will absorb that energy, and now you have a single unit, an electron whose energy is more than it used to be by whatever is the energy of the photon that it just absorbed. As I said, if the energy of the photon is just right, the electron can move up to a higher lying orbit. Let's look at our first example, the only example that I'll show you that illustrates excitation. Suppose our electron is initially in the second orbital, the second quantum state, we can say. We wish to determine what would have to be the wavelength of the photon absorbed by the electron that would elevate that electron, i.e. raise it to an energy equal to that's required in the fourth quantum level, shown here. Well, we have this equation here. On the left side of this equal sign, you have the sum of two energies. Throughout this chapter, I will represent the energy of a photon using the 1243 equation. I could use the symbol E to represent a photon energy, but that would conflict with my use of that same letter E to represent the electron's energy. So we'll just use 1243 divided by lambda to symbolize the energy of the photon. Well, we have the photon energy added to the energy of the electron in the second quantum state. Those two energies merge together to make a one, and we have then a new total energy of the electron, which will be whatever the energy is required when the electron is in the fourth quantum level, negative 0.5. So this is the before energy, this is the after energy. The two energies must be the same. We can now solve this equation for lambda, remembering that this equation will give you the wavelength in nanometers, which are billionths of meters. I solved the equation. I got lambda equals 487.5 nanometers. This is approximately, I would say, about the color green. So you shine green light of that wavelength on hydrogen. If there happens to be in your gas of hydrogen, if that's what you have, a hydrogen atom whose electron is in the second excited state, or the second quantum state I meant to say, then those photons would cause excitations from the second state to the fourth state. Now let's look at the reverse process. Well, before I do that, let me illustrate on that diagram the 2-4 transition, as we call it, transition. So our electron was in this orbit here, the second orbit there, and it's going to receive a photon and be excited up into the fourth quantum state. I won't show the photon that is absorbed by that electron. Now, in our next example, we'll look at the reverse process, which is a de-excitation of an electron, also known as the relaxation of an electron. All of the electrons that happen to find themselves in a quantum state other than one are capable of falling down into the so-called ground state, the lowest lying state, the n equal to 1 state. But they can also de-excite to some other state, not necessarily to the ground state. We'll consider this de-excitation, the 3-1 transition, the 3-1 de-excitation. Let me illustrate that de-excitation. The 3-1 transition is shown here. Electron starts out in an n equal to 3 orbital, and it makes a transition down to the ground state, n equal to 1. Now, in this process, the electron will end up with a more negative energy than it used to have. It will have lost energy. And the energy it quote-unquote lost is traveling away in the form of a photon, which has that exact amount of energy. So let's write down the conservation of energy equation involving the 3-1 transition. Initially, the only energy you have is the energy that the electron has in the third quantum level, negative 151. Later, there will be two things that have energy, the sum of which better be what you started with, which was negative 1.51. So this is the before energy. What I show here is the after energy, which is the energy that the electron will have in the first state, n equal to 1, negative 13.6, but there's something else that has energy later, and that is the photon that is wiggling away from that location where the de-excitation occurred. So here again, this is the initial energy. Right-hand side of the equation is the later total energy, which is the sum of the two kinds of energies. The energy the electron has later, when it's in the first state, negative 13.6, plus the energy of that photon that is emitted from that de-excitation location. We represent the energy of that photon using the 1243 equation again, and we solve this equation for lambda. Once and for all, we get the following result. The wavelength of the photon that is emitted during this de-excitation, during this relaxation, is 102.81 nanometers. There's very little else in this chapter that you need to understand beyond the quantization of orbital radii equation, which I presented last time, and the quantization of electron energy, which I've just presented and given a couple of examples for. You will want to check the notes to be witness to a few example problems involving excitation and de-excitation. You may want to ask questions about the practice problems dealing with these two behaviors, this one here, excitation and de-excitation, as well as quantization of orbital radii. That's all for now. Good luck on the coming exam.